Okay, first the midterm date again, once more. Well, apparently on Sunday, there is this centralized exam in the department, so you might have problem coming into the department. So we should better move it back to Saturday. Again at 9:40. Up to something like 1. And as usual, you will of course have time to finish whatever you are doing at the end. So do you have any questions before we start? If you remember last time we were studying the induction law, we had seen that if there is a changing magnetic field, that will also create an electric field. And hence we modified before in electrostatics, curl of E was equal to 0, and now this is curl of E is equal minus 1 over C dB by dt. This second term is the modification to our Maxwell's equation when we have dynamic systems that are changing in time. And this minus sign is also sometimes called the Lenz rule, which basically states that if there is a current induced by this induced electric field, the induced current will be in the direction to oppose the change that creates it. So it's back on Saturday. Now, any questions on this in the applications? No. Yeah, I mean, in the beginning of the class lecture, you can ask any questions about anything that puzzles you about electrodynamics, statics, or... Okay. So this is the question. Let us first solve the electrostatic analog of that one, which is we have a spherical object, and inside this we have another sphere, a smaller sphere. This is a cavity. So this is where we have the charge distribution. Let's assume that the charge distribution is uniform and the charge density is rho everywhere. So the question is, what is the electric field inside our sphere? Now I will also call, let's say, the large sphere has a radius A, the small sphere has a radius B. I will denote this vector as my D. Okay, so this is another problem. This is not that one yet. This is in electrostatics. Because, well, I'm not solving that one directly because the idea will be basically the same. Now, we know this proposition principle. We said that this thing is basically the same as a full sphere with a charge density rho plus, well, this is our full sphere, the cavity with a charge density minus rho. Because if we superpose these systems, we obtain our initial system with 0 charge density in that cavity. Now, let's say we are trying to find the electric field at this point. Let us call it R. Let me say this is my R. The center of my cavity is at, let's say, R2. The center of my cylinder is at the point R1. Now, we had already studied the problem of the electric field at this point. Let's say at a distance R from the center, let's call this vector the R vector. Now the electric field at that point, the magnitude, will be just the total charge inside this sphere, which is 4 pi over 3 r cubed, this times rho. This is the total charge, divided by r squared. So this is 4 pi over 3 rho r. This is the magnitude. Well, the electric field itself is 4 pi over 3 rho r in the r hat direction. So I can just write this as 4 pi over 3 rho times r vector. Now this basically tells me that the electric field at any point inside my homogeneously charged sphere is proportional to the position vector relative to the center of the sphere. So if you look at that r point r, this point, well, it is charged and its electric field will be the electric field created by these two configurations over here. The first one will create the electric field 4 pi over 3 times rho. It's the position of that point r relative to the center of the big sphere is nothing but r minus r1. Plus, well, the electric field due to this minus rho charged sphere will be 4 pi over 3 times minus rho. It's the position of r relative to the center of the cavity is r minus r2. So these r's, they will cancel each other. So the electric field will be 4 pi over 3 rho times r2 minus r1. But you see, r1 plus d is just r2 from this figure. So r2 minus r1 is just d. So the electric field in that cavity is uniform. Now let's come to the example of the book. Well, we can solve the analog in magnetostatics. Let's see, we have a cylindrical wire this time, so it's an infinite cylinder. Inside there is a cavity, another cylindrical cavity. Also infinite. So basically this is from the cross-sectional view. If you just look at from the kind of the side, this is our cylindrical wire. Here we have this cavity. Everything extends up to infinity. Now first let's solve the, let's say there is a current density running in my system. Let's say it is running into the screen and it's the J uniform constant. So this will be the superposition of these two configurations. On one, I don't have that cavity, I have the same J. On the other one, I only have the cavity, it is a wire. The current density is out of the screen and it is minus J. So inside that region, the total current density is J plus minus J, that is 0. So first I need to find, let me just find the B induction field.
Where about J? I'm not sure. It's minus, so the direction is out into the screen. So
No, direction is out of the screen.
magnitude is negative, so
Magnitude is always positive.
how about the minus now?
That just changes the direction of J. J is into the screen.
Okay.
That's how I define it. Minus J is in the opposite direction, out of the screen. Now let's see. Let me just look at this point. I will just use the Ampere's law. B dot dl around any closed loop is just 1 over C times the enclosed current. Then in this case, I can just take such a Amperian loop. So it will just give me, with the radius, let's say S, 2 pi S B S is equal to 1 over C J times pi S squared. Pi's cancel, S cancels one of them, so the magnitude of the magnetic induction is just 1 over 2C times J in the S direction. J times S. Now the direction of the B field at this point is, what's the direction? Well, so what's phi? Which direction is counterclockwise or clockwise? Okay. Clockwise. So at this point it is in this direction. Let's say this is our phi hat direction. BSB will be 1 over 2C JS in the phi hat direction. Well, let me write this in a different form. Well, I already have the, let's say this is, let us call this is the S hat vector. And J hat is into the screen. So J hat cross S hat, what is the direction? No, J hat cross S. S hat cross J hat is in this direction, it's minus phi. So J hat cross S hat is in the phi direction, phi hat direction. So phi hat is J hat cross S hat. So this will be equal to 1 over 2C J times S J hat cross S hat, or 1 over 2C J in the J hat direction cross S in the S hat direction. Or this is equal to 1 over 2C J cross S. Just keep in mind this S vector is not the position vector of my particle. S vector is the projection of the position vector to the XY plane if you just take the axis of your cylinder as your Z axis. Okay? So now this is for one cylinder. We will basically do the same trick. Let me call the position of the center, the projection on the XY plane of the position of the central axis to be S1. This is S2. Let's just pick some arbitrary vector point over here. This is S. These vectors do not have their Z components. So then B at the point S will be equal to the B due to this full wire, which is 1 over 2C J cross. Well, the S appearing over here is the position vector of my point relative to the center of the wire, just like in the cylinder example. So in this case, it will be S minus S1. Plus 1 over 2C, now the contribution to this part, well, the current there is minus J, and the position of that point relative to the center of this cavity is S minus S2. So S's again, they will just cancel. This is 1 over 2C J cross S2 minus S1. Again, you see the B field is uniform in this cavity. So basically it will, now let me replot it. This is my wire, here is my cavity. J is going into the screen. S2 minus S1 is just this vector. And J cross S2 minus S1 is in this direction. This is these are my magnetic field lines. Magnetic induction lines. It's uniform. So their separation, their density is also uniform. Now this is just a special case in which, just like in the previous example, it was the electric field. In this example, it is the magnetic induction field, and they just turn out to be proportional to the positions relative to the center of our system. So that when you take this superposition, you just get the relative separation between the center of the wire and the center of the cavity.
How do we resolve the contradiction between when you have infinite solenoid?
Infinite?
Solenoid. The magnetic field does not move between the solenoid and the loop around the solenoid.
But still there is the electric field, right? So you see, we had this example. If you just take an infinite solenoid with current running around it, we know that there is a uniform B field inside. Outside the B is 0, and B is given by mu 0 I times n magnitude. So if you just, let's say, assuming that you change the current, but the relation between the B field and the current still remains the same. In that case, there will be an electric field generated everywhere. So if you just imagine, let's say, such a loop, we know that E dot dl, let's say the loop has a radius S, R, capital R, E dot dl will be just minus, let's say this has the radius A, minus d phi B by dt, which is minus d by dt pi a squared, which is the area, times mu 0 I n, and it is I that is changing this minus pi a squared mu 0 n di by dt. On the other hand, E dot dl will be just E at the point R times 2 pi R, so E of R will be equal to minus pi a squared mu 0 n over 2 pi R times di by dt. Well, the critical thing is this is non-zero. There's an electric field generated there. Although there's no B field, we said that outside our solenoid there's no B field. Nevertheless, there is an electric field generated. So how come? If it is the change in the B field that's creating the electric field, well, there's no B field to change to start with. Well, basically you can look at it in two different ways. One is, if you don't want to use the analogy of the motion of the magnetic field lines, then you can say that, okay, the infinite solenoid is not really a realistic example. So you have to, you see, the problem is, if you have an infinite solenoid, it has infinite energy. Changing the current would mean you are providing infinite energy, which just doesn't make sense, so it has to be finite. If it is finite, outside B is non-zero. So that's one way of looking at it. Now, if you would like to use the analogy with the moving B lines, you can say that, okay, the B lines, they have to be closed. They are formed by closed. They have to be closed. So they start both inside and outside, just very close to your solenoid. And then inside the number of B field lines increases as it moves away from the wires. So it is increasing the B magnitude inside. The B line outside, it just moves to infinity. Since it goes to infinity, the B field is always 0, but nevertheless it crosses your wire, your loop. And this motion of the B field lines relative to a point is what is creating the electric field. So this is just another way of looking at it.
So basically what we're saying here is that in electrodynamics, the B field is not zero, even if we have anything.
No, B field is always 0, even in dynamics. If I is changing slowly, let's say, B field will be always 0. The B field lines that are generated, they just go to infinity and dilute the system.
And here was no zeros.
Nope, sorry. 1 over C. Well, every day I'm switching my units, sometimes within a day. Other questions? So let's summarize what we know already. Divergence of D. For pi rho. Curl of E. Divergence of B, curl of H. Okay, this is what we had discussed. Now, we had also just shortly, briefly mentioned that there is an inconsistency in these equations. They are not consistent with the fact that d rho by the dt plus the divergence of J should be equal to 0. This is charge conservation. Now, how do we see that? Well, just put it back. D by dt, rho instead of rho, we can use 1 over 4 pi, the divergence of D, plus the divergence of J is C over 4 pi, curl of H. This should be equal to 0. Well, the second term is automatically 0 because the divergence of a curl is 0. But D can be time dependent. There is nothing that prevents the time dependence of D. So this is where these four equations, in their current form, they are not consistent with the charge conservation. Now, the easiest fix to this would be just to add by hand here. Well, just to cancel the divergence of D, the time derivative, just add minus 1 over 4 pi del D by del T. Whereas the divergence of the derivative is the derivative of the divergence. So if we add this by hand, I repeat, everything is consistent. Do you agree?
How does this modify these modifications?
Well, let me just put the minus sign, where the continuity has a minus sign over there. So here I don't have that minus sign. So this basically tells me that in J, I basically add this term. So this equation just becomes plus 1 over C del D by del T. This is what's called the displacement current. Now, these are the complete Maxwell's equations. Now, in a simple system, at least, we can actually see that we have to add that term, and that term does solve our problem. For example, just take this straight wire example.
It's 1 over 4 pi.
No. You see, this is my J. This is the contribution to J. But J is multiplied by 4 pi over C. So 4 pi's cancel, I'm left with C. So basically, all of this expression should be my J. So that I end up having, this is my rho, del by del T of rho minus the divergence of J is equal to 0. But if you look at this equation, J is multiplied by 4 pi over C. So I have to multiply that additional term also by 4 pi over C, and that gives me that factor 1 over C.
If it's in J, then why do we add something?
It's not in J origin. I mean, you see, we have to replace J by this thing over there. No, hold on. Am I doing it correct? No. You see. Okay. So let me just add. This is a plus sign. So if the rho is decreasing, there is a positive J. So this is a plus sign. Here I get a minus sign. Okay. So J is equal to C over 4 pi curl of H minus 1 over 4 pi del D by del T, or curl of H is equal to 4 pi over C times J plus 1 over C del D by del T. Now let's see a simple system where this is actually correct. We have our infinite wire. It extends to infinity. We don't really care what it does at infinity, because as long as it's far away, nothing should change in our position. So we already know that in this region, we can take such a loop, and around that loop, B dot dl should be equal to mu 0 times I, and I can just take I to be constant. So let's just assume I create it such that I is constant. So in this region, I have my magnetostatics. So this should be equal to I over C, or 2 pi r times B should be equal to, if this has the radius r, this is I over C, and B is equal to 1 over 2 pi C I over r. Okay, great. So what is I? I enclosed. Let me just write I enclosed. What is I enclosed? How do you determine I enclosed? Well, that's obvious over there, right? But kind of I enclosed is nothing but the integral of J over some surface S. Now the critical thing is that here we have a loop integral, and that closed loop should be forming the boundary of S, a boundary of our surface. So that if this is integrated over our surface S, this loop integral is over the boundary of S. Now, the thing is, there are infinitely many surfaces whose boundaries are the same loop. So this is one such example. Another such surface who has exactly the same boundary is this one. Just a bag. You can stretch it. Now let's just imagine that this wire, we don't really care what it does at very far away points. It shouldn't be affect what's happening here. And this wire just goes to a far, far away galaxy. And in that galaxy, the wire has a capacitor. So this is our galaxy. This is the far, far away galaxy. in a galaxy far, far away. So whether there is a capacitor there or not I don't really care. I shouldn't care. Nothing should be changing in my region. But let's see, now this is a mathematical surface that I'm integrating over this S. So I can just extend it up to this galaxy far, far away. Now at every point of this new surface, J is 0. Since J is 0, I enclose just turns out to be 0.
Why J is 0?
Well, you see, J is the flow of charges. On which part of this surface there is a charge moving from one side of the surface to the other side? So no charge is moving from one side of my surface to the other side. You see, if I took this surface, if I had taken that red surface, J is 0 almost everywhere except at this point, over here. Because at that point, charges are flowing from one side of my surface to the other side of the surface. So there's a current density over there. But in this new surface that extends to the galaxy far, far away, no charges crosses my surface. So on my surface, there is no charge flow. On my surface, there is no current density. But there's something else that is flowing through my surface, and that is the electric field. Just ignore any kind of matter effects. There is an electric field flowing through my surface, which itself is changing. So instead of the enclosed current, which is kind of the flow of charge, I can replace it somehow by the change in the electric field. Because as the current is flowing, there will be more and more charges accumulating on the capacitor, and hence the electric field will be increasing. So I can relate the change in the electric field to my current. Now the electric field in the capacitor, let's say the magnitude, this is equal to, well, just imagine we have a flat capacitor, infinite plates, or very large plates.
Q over C.
Q over C? No. Q over A times D. Q over A is the area of the capacitor. Or Q is equal to the electric Q over D is equal to E in the capacitor. Or there's not even D, it's just sigma. No, 2 pi sigma. Hmm? 2 pi sigma. You see, divergence of E is equal to 4 pi rho. So we have the 2 pi sigma. 2 pi times Q, or Q is electric field in the capacitor times A times 1 over 2 pi. Or Q is nothing but the integral of E dot ds 1 over 2 pi over my surface. But you see, if I take dq by dt, how is it related? I can relate it to the current I. So I is dq by dt or minus dq by dt. dq by dt is nothing but my I. So you see, I can write the enclosed current as the integral of J over the surface, or 1 over 2 pi dE by dt over my surface. Now this is 4 pi. If you have an infinite plate, it is 2 pi over 2 pi times sigma on both sides. If you have two plates, you have 4 pi over sigma between the plates and 0 outside. Now, you see, if you take, for example, this red surface, over the red surface, the second term is 0. There's no electric field over the red surface, but the J dot ds is just the I enclosed. Now, if you take this bigger surface that goes to the other galaxy, over this surface, J is always 0, but this integral over here is equal to I. So the sum is kind of independent of whether I take the red surface or the other huge surface. And kind of my laws should be independent of which surface I choose. And this kind of concludes that the B dot dl, now it has to be replaced by 4 pi over c, 1 over c. Now 4 pi over c. Four pi over c, J dot ds plus 1 over c dE by dt. Or if you just write this also as the integral of the curl of B over ds should be equal to 4 pi over c J dot ds plus 1 over c dE by dt. And hence you recover this law. Of course, this is in medium. If you don't have any medium effects, H is just B and D is just E. So this kind of completes our Maxwell's equations. Plus, of course, we have other equations that define H and define D, etc. And we have the continuity equation, we have the force law, the force density, let's say, acting on a given charge distribution would be just rho E plus J cross B. So this should be enough to describe everything that we just observe in everyday life. All the phenomena are just describing these equations. Now, what I would like to discuss in the next hour is conservation laws. Okay, we had already seen that we can identify the energy in an electric field. That was one thing we had discussed. We didn't really discuss the energy in a magnetic field, in a B field. And we also had this problem about the action-reaction pairs. So in Newton's law, there are no action, we had seen that if we have these 2 point charges, the forces that they will feel will definitely not form action-reaction pairs. And if there is no action-reaction pair, momentum should not be conserved. The only way out is we should assign momentum to the electromagnetic fields itself. So how can we identify the momentum of the electromagnetic field? Well, do you want a break? Okay, that we will do after the break.